If you've ever looked up at the sky and felt like you had a pretty good map of our solar system, well, get ready for a bit of a shock. Because right now, something is zipping through our neighborhood that basically breaks all the rules.
It really does. It's not from around here.
Not from the Oort cloud, not from the Kuiper belt, no. This is a genuine, confirmed visitor from another star system entirely.
And it's not just passing through, it's, delivering this incredible gift, a sample that scientists are scrambling to unwrap before it just speeds away forever. That's the perfect way to put it. Today, we're doing a deep dive on this incredibly rare thing, the interstellar comet known as 3IATLAS. And for you, our mission today is pretty straightforward. We're going to unpack the sources to really understand what this object is, why it's such a massive deal for science, and what its journey is telling us.
And it's telling us a lot already. Okay, so let's unpack this. We have to start with the name. 3IATLAS. What does that string of letters and numbers really tell us?
Well, the name itself is the whole story, really. The most important part is that letter I.
I for?
For interstellar. It's the official designation. It means this object, 3IATLAS, has been, dynamically confirmed to come from outside the sun's gravitational pull.
From id space.
From interstellar space, exactly.
And that number, the 3, that also carries a lot of weight, doesn't it? This isn't the very first one we've seen.
No, but it is only the third, just the third. We had 1 Oumuamua, which was that strange, tumbling, cigar-shaped object.
Right, the really mysterious one.
Then we had 2I Borisov, which looked a bit more like let's say, a conventional comet. But to see a third one, it just highlights how sporadic these visits are. Each one is a fleeting, one-time only delivery.
A sample delivery. I like that. So speaking of delivery, how did we even spot this thing? The sources say it was first seen on July 1st, 2025. Tell us about the ATLAS part of the name.
Right, so that's the system that found it. It stands for the Asteroid Terrestrial Impact Last Alert System.
Okay, so its job is to look for things that might hit us.
Exactly. It's a robotic telescope system, mainly in Chile, scanning the sky for potential impact threats. And in doing that, it just happened to find this spectacular object hurtling through our system.
And this is where the physics gets really fascinating, and frankly, where the urgency comes from. The sources keep using terms like unbound and hyperbolic trajectory.
Yes.
Can you break that down? What does that actually mean for this object's future?
Sure. So think about everything in our solar system. The planets, asteroids, comets, even the ones from way out in the Oort cloud. They are all gravitationally bound to the sun. They're in orbit.
They're stuck here with us.
They are. But a hyperbolic trajectory, well, that means 3IATLAS is just moving too fast. It's like it has escape velocity.
So the sun can't grab it.
The sun's gravity just can't capture it. It's going to swing past the sun, get a little gravitational slingshot, and then accelerate right back out into the void.
So zero chance of a return visit. It's like a high-speed train just blasting through the station. We get one look.
One look, and then it's gone forever. That one-shot nature really defines the whole scientific mission here.
Okay, so that brings us to the big so what question. What is the prize here? I mean, how different can the chemistry of this one comet really be from the thousands of comets we've already studied in our own solar system?
That is the exact question driving, billions of dollars in observation time. Our own comets are fantastic, but they all formed from the same primordial cloud of gas and dust as Earth did.
They're all from the same recipe book.
Precisely. 3IATLAS, on the other hand, it's a page from a completely different book. It gives us material that formed around another star in another part of the galaxy. We're hunting for chemical differences.
Like what, specifically, what kind of discovery would just, blow up our current models of how planets form?
Well, we're looking for the signature of a different stellar nursery. For instance, the ratio of carbon to oxygen. Or maybe the abundance of certain volatile ices, like carbon monoxide or nitrogen ice. In our system, our comets are mostly water ice. That's because of where they formed relative to our sun's heat. If 3IATLAS is, say, packed with super volatile ices, a coat-to-water ratio 10 times higher than our average.
Then that would suggest it formed somewhere much, much colder.
Extremely cold, either much farther out in its home system, or maybe its parent star was just chemically different from our sun.
So this is a real chance to stress test our theories, to compare the building blocks of two totally separate star systems.
Exactly. If it looks identical to one of our comets, that suggests planet formation is, pretty uniform across the galaxy. But if we find wildly different signatures, it means the starting conditions for stars can vary a lot more than we thought. That would be a huge rewrite for the textbooks.
Let's talk about the observation window then, because as you said, the clock is definitely ticking. When did this thing get closest to the sun?
It reached its closest point, which we call perihelion, on October 29, 2025.
October 29th, so that's already happened.
That's past, yes. And that was the moment of maximum heat, maximum activity, when it should have been outgassing the most.
And what about its closest approach to us, to Earth?
That's coming up very soon, December 19, 2025.
And just to be clear for everyone listening, when we say close in space terms,
Yeah.
we're not talking about any kind of danger.
Oh, no, not at all. It's passing at a very safe clip. It'll be about 270 million kilometers away.
So plenty of distance.
Plenty. Far enough to be completely safe, but close enough for us to get a fantastic look. But because it's moving so fast, that December window is absolutely crucial. We have to grab all the data we can right now. Which brings us to probably the most interesting detail in the source material. This unusual brightening behavior. What does that mean? How is it acting differently from a normal comet? Typically, a comet brightens on a pretty predictable curve. As it gets closer to the sun, the ice heats up, it sublimates, turns from solid to gas, and that creates the glowing coma in the tail.
Right. More heat, more brightness.
But 3IATLAS started brightening way too early. It was getting significantly brighter when it was still quite far from the sun, which implies, well, it implies its composition is different. It's got some highly volatile stuff in it.
So if a normal comet is like a block of water ice, this one might have pockets of, say, dry ice or something even colder that's boiling off much sooner.
That's a perfect analogy. If you have methane ice or carbon monoxide ice, those turn to gas at temperatures far, far below what water ice needs. So a sudden surge in brightness, way out in the cold, points directly to these hypervolatiles.
And that's exciting, scientifically.
It's very exciting because it's a strong clue that the environment where it formed was probably much colder than where our own comets were born.
But doesn't this unusual brightening also pose a risk? I mean, couldn't a sudden burst of activity mean it's falling apart?
Absolutely. That is the other side of the coin. The sources are very clear that astronomers are watching for fragmentation.
So it could just break up.
It could. When a comet's nucleus breaks, it exposes all this fresh new surface area to the sun, and you get this huge, dramatic spike in brightness. It would be an amazing event to see, but it would mean our short window to study it just got even shorter. It would essentially dissolve.
Wow. So given this race against the clock, what tools are we actually using? I see mentions of the heavy hitters, like the James Webb Space Telescope. What's its specific job?
The JWST is critical here. It operates in the infrared, which is key. That lets it get a precise chemical fingerprint of the gases boiling off the comet.
So it can tell the difference between water vapor and, say, carbon monoxide.
Exactly. It can distinguish between water, CO, CO2, all those complex molecules. Webb is the one trying to measure those crucial isotopic ratios we talked about earlier.
And what about Hubble? Why is the Hubble Space Telescope still a key player here?
Hubble is the imager. It's our high-resolution eye in the sky. Its job is to look at the structure, the shape of the coma, the jets of gas shooting off the nucleus, and most importantly, any visual evidence of it breaking up. If it starts to crack, Hubble is the one most likely to see it happen.
What's really fascinating, though, is that it's not just telescopes in Earth orbit. The sources mention China's Tianwen-1 Mars orbiter is also being used. Why look at it from Mars? What's the advantage there?
That is a fantastic point, and it shows you how global this effort is. It's all about getting a different angle, a unique viewing perspective. When a comet's tail forms, it always points away from the sun. For telescopes near Earth, that sometimes means we're looking straight down the tail, which makes it hard to study.
Ah, so from Mars, you're looking at it from the side.
Exactly. An orbiter at Mars is way off the Earth's sunline. It gives researchers a completely different geometric view. They can study the dust in the tail, the structure of the coma, without all that, line of sight interference. It's a truly comprehensive approach.
So you just got the deep dive on 3IATLAS, a scientific time capsule, basically delivered to our doorstep from an entirely different star system. A fleeting event that has, for now, completely captured the focus of our world's observatories. So what does this all mean? We've established that the universe is, well, it's constantly sending us these little samples. But the urgency of this hyper-fast visitor just reinforces a profound idea. Our entire understanding of how stars and planets form is really dependent on these rare flybys.
Right.
This short, precious window is maybe the only chance we'll get in our lifetimes to study the raw, untouched building blocks of another solar system up close. And as 3IATLAS speeds away, moving too fast to ever come back, it leaves us with one powerful question. when rooted in its very strange behavior. Since that unexpected brightening suggests it carries materials we rarely see in our own comets, what crucial detail about its home, the temperature, the distance from its parent star, or the density of its birth nebula are we hoping to finally measure from that hypervolatile signature before this object disappears into the vastness of the galaxy forever?
That's something for you to mull over.
We'll catch you on the next Deep Dive.